Hello everyone, this is Huang from TAL Education Group. Today, I'm going to present you our paper, Multimodal Learning for Classroom Activity Detection. Hope all of you have a good journey with me. First, let me introduce you about the background of our research. Teaching quality assurance has been a popular topic since 1980s. The prior researchers have proven that by analyzing the students' and teachers' behavior, educators could notice and correct the mistakes that teachers and students made during the class. Through the accumulated notifications, both teachers and students could receive improvements in their teaching skills or studying efficiencies. However, the concurrent approaches for teaching quality assurance are mostly built with the fine-grained classroom activity logs. For example, both teachers and students speaking details, including time and content, are the prerequisite for the most of the analyzing work. This fact sets a barrier for the implementation of the rated works. In fact, unless both students and teachers are equipped with the separate microphones, the fine-grained classroom activity information will be hard to get, and students within such scenarios, which is quite normal, will be difficult to receive any benefits from these researchers. Based on that background, our research team set our goal to detect the classroom activities for the audio recordings with a mixture voice. To be more clear, we hope to segment the original mixture voice recordings into the single speaker clip. Besides that, the speaker role for each segment should also be identified at the same time. Although the goal of our research is clear and straightforward, the task is still facing a lot of challenges. For example, the single modality information is not enough for both subtasks at the same time. The vocal information is valid for splitting the single speaker clips, but is usually useless for identifying the speaker's role. On the other hand, semantic information is effective in role identification, but is weak in speaker segmentation. Besides that, the flexibility and the robustness of the algorithm should also be strong enough to guarantee that the algorithm is compatible with different scenarios. As we mentioned previously in the slides, our classroom activity detection task mainly has two components, speaker segmentation, which is also known as speaker diarization, and role identification. In recent studies, these two components are usually treated as separated tasks. The speaker diarization task is always modeled with an audio-based algorithm, while the role identification model is usually built with the semantic information from the conversation sentences. Then, a simple workflow is designed to connect the two models. Although the two-stage approach has been proven to be useful and easy to be implemented, the effects of this algorithm are also obvious. First, the prediction errors are accumulated throughout the pipelines. Besides that, the optimization for separated stage model is lack of efficiency. And at last, the cross-modality information will always be missed due to the separate stage design. In order to correct the shortcomings of this approach and make a better use of the multimodal information, here we proposed our algorithm with the multimodal learning idea. Before the formal presentation of our method, I hope to show you a related example of our data. I hope it will be helpful for you to understand the intuition of the method. Here, we first process the classroom recordings with an automatic speech recognition system, aka ASR, and the sentences of the student-teacher conversation is shown as above. The color of the text boxes represents the role of the speaker. Blue means teacher and yellow means student. From the plot, we can find these sentences are very informative, and some of them even provide very strong evidence indicating the speaker's role. Take the third sentence as an example. It says, "How's your day in school?" After understanding the semantic information between the words, we can easily judge that the sentence should be spoken by the teacher. However, Some of the other sentences, like the first two greeting ones, are actually hard to be determined, since both students and teachers speak them commonly. To solve this problem, we come across the idea that we should introduce the text information from the other sentences to help. For example, if the first sentence is hard to judge, then we need to use the third sentence for help. The reason for us to consider the third one instead of the fourth is that the first sentence shared a similar voice with the third one. Here, the exotic feature acts as a bridge that wisely connects the semantic feature across different segments and helps the model to make the correct prediction easily. After seeing the last example, I hope all of you already understand the idea of our paper. And here I'm going to introduce you the details of our framework. First, exotic and semantic features of each segment are generated through two separate pre-trained embedding models. Both of the features are then fed into a multimodal attention layer. Within the layer, exotic features serve as both the query and the key, and text features serve as the value. When the prediction starts, the similarities between all segment pairs are calculated and then transformed into attentional weights. These weights are multiplied with the semantic features to generate the fused embeddings for all input segments. Outside the attention layer, we design a residual connection through concatenating the fused embeddings with the text ones. After that, we employ the bidirectional LSTM layer to extract the sequential information between the segments. At last, a fully connected layer is used to generate the final predictions. Apart from the framework, we also introduce an attentional regularizer to penalize the cross-row similarities between the segments. After applying this regularizer, the influence of the irrelevant segments are suppressed, and the model's loss function converges much faster. The loss function we design is composed of two parts. First one is standard binary cross-entropy loss, and the second one is the attention regularizer that we introduced just now. We set a hyperparameter beta to balance the effectiveness of the two parts. We collect two types of data for our experiment, and we name them as online and offline. The online set contains 400 online class recordings from a third-party education platform, and the offline set includes 15 recordings from the offline classrooms. The label of each segment is either student or teacher. For those segments with mixture voice, we label them as the dominant activity types. The two pre-trained embeddings models we used for our exotic and semantic features are Votovac and LSTM-based speaker embeddings. The train set we used for training our model is 350 cores from online recordings. The total duration of them is about 350 hours. And we used the remaining 50 online and 50 offline videos as the test set. To prove the effectiveness of our algorithm, we set a few baseline models for our experiments. The first 5 models are the variants of our proposed framework. The top 4 change the inputs of the algorithm from both exotic and semantic features into single modality embeddings. And some of the network structure are also modified. The 5th model replaces our multimodal attention layer with the simple concatenation. The last 2 models are built with 2-stage pipeline algorithms, but incorporate with different first-stage models. Spectral is using a spectral clustering algorithm, where UISRN uses the UISRN classification model. From the resulting table, we find that our proposed algorithm received the best performance on both online and offline datasets. Besides that, by comparing the 5th ones with ours, we can easily draw the conclusion that the multimodal attention layer played an important role in improving the model's learning ability from the multimodal data. In other words, in this paper, we proposed a novel multimodal learning network for the classroom activity detection task. And the algorithm may also be compatible with similar problems. For example, the agent-customer separation in phone calls. In the future, our researchers will focus on the robustness of the algorithm in different scenarios. Well, that's all for our paper's presentation. Hope all of you have enjoyed it. Thank you for watching. Hope you have a good day.